Math and Beats. Continuing with the derivative discussion, we are going to focus on a couple of examples here in this video of just showing how to use the limit definition of a derivative to find a derivative function. Now, in the previous video, if you're following along, we went ahead and explained the concept of a derivative function and all of that stuff that goes along with it. But now we're going to use the definition in this video. So we're going to get going here. All right, so remember, just to recall, the limit definition of the derivative function. So, of course, given some function y is f of x here, so you got a function y is f of x, it's doing its thing. Then the derivative function right down here, remember that's pronounced f prime of x, that's our derivative function, is defined to be the limit as h goes to 0 of f of x plus h minus f of x divided by h. So remember, that's just given any x location for which this limit exists, go there, make a secant line out to some other point on the graph of the function, and that input change we denote by h, and you let that input change go to 0, and the slopes of the secant line of that function approach the slope of the tangent line of the function at any value of x for which this limit exists, and all of those defines the derivative function f prime of x. So we're going to use that limit definition right there on the screen to find some derivatives of some functions. All right, so the first example here, we're going to use that limit definition of the derivative function to find our derivative function f prime of x, given the function, specifically here, is just f of x is x squared. So again, let me just write it here on the top so we have it for reference. F prime of x is limit as h goes to 0 of f of x plus h minus f of x all over h. So we got to find that. So we have f of x, we have the formula for it, right? It's x squared. So usually something nice to do is just go ahead and figure out what f of x plus h is so we can use it in this derivative formula. So what is f of x plus h here? Well, again, we have the formula here. F of x is x squared. So I'm just going to replace x with x plus h and obtain x plus h quantity squared. All right, now, because we have to subtract f of x from this f of x plus h within our limit definition, it might be worthwhile just to expand this real quick. So just binomial expansion squared gives us x squared plus 2xh plus h squared. So there's our f of x plus h. Let's go ahead and compute the limit definition of the derivative now. So therefore, f prime of x going to be limit h goes to 0. All right, remember, up here on the top, f of x plus h, which we just found was x squared plus 2xh plus h squared. So x squared plus 2xh plus h squared, there's my f of x plus h, minus the function x squared, because that's f of x, so minus x squared, all divided by h. So one thing we immediately see is that x squared minus x squared disappears, right? So this is just the same as the limit h goes to 0 of 2xh plus h squared all over h. Now, as h goes to 0, numerator and denominator both go to 0, so we have that indeterminate form. So we better do some type of algebraic manipulation here. And notice the numerator has a common factor of an h. So go ahead and write this as limit as h goes to 0 of h times 2x plus h is left over all over h. And now we see that common factor of h disappears. Goodbye. And hence, this is just the limit as h goes to 0 of 2x plus h. So let's just write that. Limit h goes to 0 of 2x plus h. So now we don't have an indeterminate form. We can take this limit, and so h is the thing that's changing, of course. H goes to 0. As h goes to 0, well, h goes to 0. And what are we left with? 2x. Thus, our derivative function here, f prime of x, is 2 times x. That is the function that gives the slope of x squared at any value of x for which this limit exists. And of course, this limit will exist for all x. So that is an example of using the process of the limit. Let's go ahead and take a look at a nice, beautiful picture here, right here, which is showing exactly what's going on. So blue graph, y is x squared, the function of consideration. The green graph, that is the tangent line of y is equal to x squared at whatever x we're at. So that blue point right there is our x value. And then the red graph is the function f prime of x, which is equal to 2x, remember right here? F prime of x was 2x. So all of this is being shown at the same time. And all I'm going to show in this diagram, I'm going to move the x around. So for instance, let's just go to as close to x is 0 that we can. Maybe right around there, right? Getting close. But as we can see, the value of the derivative function, which is 2x here, is 0, close to 0. And then if you think of the tangent line, 2x squared, the green graph here, what's the slope of that line? Well, as I get close to 0, that line seems to be horizontal, right? So that slope is 0. So these are all kinds of things we want to keep in mind as we move forward. We're going to talk about it more in depth as we go through this Calculus 1 discussion and derivatives. But this is that first opportunity to kind of see it at play, right? Notice on the right side of 0, this parabolic function x squared is increasing. And my slopes, this red line here, right, all have outputs that are above the x-axis. They're positive. The slope of those corresponding tangent lines, also positive. Right? So it's all consistent with each other. And something similar can be said to the left of 0. Is that over here to the left of 0, that parabola, y is x squared, is decreasing function. And we can see the slopes of the corresponding tangent lines are negative over there. And thus, the function y is equal to 2x has output values that are negative below the x-axis because they're negative. So that derivative function here, y is equal to 2x, that's a function. And every output value it has is showing us the corresponding slope of the tangent line at the same value of x on the graph of y is equal to x squared. Now you may have been noticing fall around, I just had a little counter down here for every value that we're at, just showing the output values. So there's one example. We'll do one more before we wrap up the video. So let's do that one more. All right, another function. Notice this function here, w of t is the square root of 2 minus t. Again, we're going to find the derivative function, w prime of t, using the limit definition of the derivative function, the same definition we just used. Really only difference here is that, you know, a lot of times by convention we use x as the input variable, but this function has an input variable t. So the only really thing that changes is use the same exact formula, but instead of using x, use t. So in this case, w prime of t here is going to be, again, limit as h goes to 0, still letting h be that horizontal distance between our input value t and t plus h. So what's the difference quotient we take the limit of? That's going to be w t plus h minus w of t all over h here. That's just a slightly different notation, but it means exactly the same thing. Input value is t rather than x, and our function is w rather than f. So let's go ahead and figure out what w of t plus h is. W of t plus h gonna be, we'll here just replace t with t plus h. So we get square root 2 minus, now here be careful, the quantity t plus h, right? That minus sign is going to get distributed to both those terms, And when we do that, we get the square root of 2 minus t minus h, distributing the negative sign, which isn't absolutely necessary, but might as well. All right. Therefore, w prime of t, the derivative function of w, is limit h goes to 0. All right. W of t plus h, we just found it, square root 2 minus t minus h, minus w of t, so that's square root 2 minus t, all over h. So that's that limit we got to find. H is the thing that's changing. T is the variable, the input of the function. So numerator, notice, goes to 0 as h goes to 0. And so is the denominator. We got that indeterminate form again. And this is one of those limits that we should hopefully be familiar with at this point, where we see sums or differences of radicals in the numerator or denominator. And in that case, we want to try to rationalize. So let's multiply by the conjugate of the numerator here, which is the square root 2 minus t minus h, and then just switch that sign between the roots, right? Plus the square root of 2 minus t, all divided by, of course, the same thing, square root 2 minus t minus h, plus square root 2 minus t. All right, so when we multiply that out, of course, we're going to get limit statement again here, still taking the limit as h goes to 0. Remember how that numerator works? That's like multiplying the difference of two squares, and so the radicals go away and a minus will be in between. The first term will just be square root 2 minus t minus h times itself, which is 2 minus t minus h, and then minus the quantity square root of 2 minus t times itself. So that's just minus the quantity 2 minus t. All of this divided by h times that square root 2 minus t minus h, and then plus the square root of 2 minus t. You could choose to multiply the denominator out, but there's no real reason to do that yet, because really we're trying to get that h to disappear through valid algebraic methods. Now in the numerator, notice what's going to happen. I'm going to perform this subtraction right there. 2 minus 2 is goodbye. A negative t minus a minus t, that's negative t plus t, that's goodbye. So hence we get limit as h goes to 0 of negative h in the numerator divided by h times, again, that sum, square root 2 minus t minus h plus square root 2 minus t. And then you can see those h's are going to cancel out. And finally, we're left with limit h goes to 0 of now a negative 1 in the numerator, all divided by square root 2 minus t minus h, and then plus square root 2 minus t. And now you know that h that was causing the problem in the numerator and denominator, making it go to indeterminate form, no longer happens, right? We don't have indeterminate form anymore. So we let h go to 0, and the only place that I see a h is right there. That's going to go to 0. And so what am I left with? Negative 1 over square root 2 minus t plus the square root of 2 minus t. And so if you just add the denominator terms up, we get negative 1 over 2 root 2 minus t. Bam! And that is our derivative function, w prime of t here. And that is the function that gives the slope of the original function w at all values of t for which that limit exists. So again, we're going to have another diagram to help us here. Oops, let me bring that back up. So what we see here in the diagram, again, the blue graph is the graph of w. That's the square root of 2 minus t. The red graph is the graph of its derivative, w prime of t, which we just showed a moment ago, was that function that we see right above, and that is a negative 1 divided by 2 times the square root of 2 minus t. So that's that red function. That's w prime there. The green graph, again, is the tangent line at the corresponding value of t. Okay, so of course, as we move around, we can see all the way from negative infinity up to 2, the function itself, the blue graph, which is square root 2 minus t, it's a decreasing function, right? And so the red graph we see, which is the derivative function w prime, notice it's always below the t-axis, and it's negative for that reason, right? So as I move over here, right, we can see negative slope, and it's not very steep, right? As I move along, I actually start getting a little steeper. And then as I get close to 2 here, because of course 2 is the end of the domain for the function square root 2 minus t. This function's not defined to the right of 2, at least for real value outputs. And so notice as I get close to that location, the function's slope seems to be becoming infinitely negative. And indeed, that's what's happening. And so, that's part of the reason why we usually just talk about derivatives over open intervals, because at endpoints, funky stuff happens like this. And so that's all consistent with each other. It's consistent with the formulas we found. And hopefully those couple of examples there of using the limit definition to find the derivative function gives you a nice place to start trying some other ones on your own. And on that note, math and beats, we're done. Until the next one, I'm out.